So we're going to carry on talking about pipe flow today. The main points, I suppose, as you know, are that we can write Bernoulli's expression, and we end up with an energy equation which allows us to write things between 2 points in a pipe system. I'll reiterate kind of the important parts of that. The energy equation can include an expression for the pump head. It's written between upstream and downstream by convention. It has to be that way. And we have components, of elevation, pressure head, and velocity head, and components related to major losses, the sum of them, and minor losses. And typically the minor losses are written as something like a loss coefficient times a velocity squared term. And so the supposition of this is that they're always turbulent within the fitting, and therefore we don't have to worry about what the Reynolds number is. For the major losses, which are small incrementally but typically over a long length, we can write as a friction factor, the length to diameter of the pipe, and again the velocity squared term in the fitting. So this is always the velocity in the fitting or in the pipe, not at points 1 or 2. And we've drawn this thing as our standard figure. So that's really what we're dealing with. So this is velocity at point 1, this is velocity at point 2, this is velocity in the pipe or the fitting. This is the head loss. The head loss in the friction, it depends on a friction factor, which we know is in terms of a Moody's chart, which is a function of Reynolds number versus this friction factor magnitude. And we know there are basically 3 regimes. Bless you. One is laminar, when the friction factor is equal to, for a circular pipe anyway, 64 over Reynolds number. There's a transitional period. This is laminar, transitional period, and then turbulent. And so the important features of these Moody charts are that if, what is this? This is the direction of increasing roughness, epsilon over pipe diameter. And so there are 2 important features, I guess, with this. And that is, as you get rougher pipes, you get larger friction factors, which kind of makes sense, right? It's more difficult to push fluid along a very rough pipe than it is a smooth pipe. And also the transition, if you like, from laminar to turbulent occurs progressively earlier with increasing roughness. And so we've seen that in our figures. But perhaps it's easier just to not look at the Moody chart so much, but just get a concept of, or a feel for what's going on. Is that you have this laminar behavior where the friction factor is always a function of Reynolds number, which is sometimes a problem, because if it's a function of Reynolds number, and for instance you don't know what the flow rate is, then you have to iterate to get a solution. It's much easier, surprisingly, perhaps, if you have a turbulent flow, because the friction factor is just a constant magnitude. Right? This line here is horizontal, and so it just means a constant magnitude, whatever the value of the Reynolds number. And so it ends up being sometimes an easier one to solve. And I suppose the only other thing that we should remember is that in terms of our pump heads, the pump head is equal to the power in watts. So I put a dot because power is rate of doing work, right? Newton meters per second, so watt is a Newton meter per second. And it's can write a variety of different ways. But we could also write it as mass flow rate multiplied by G, I think, right? Which is also the same as volumetric flow rate times unit weight of water times. So this is power. So it's in watts. So that's basically it. I mean, that's the energy equation, which we derived couple of weeks ago, I guess a few weeks ago now. Has to be written between upstream to downstream. Remember that. And if you do that, then if the pump head is positive, it's energy you're putting into the system to pump. If it comes out as negative, it's energy you're getting out of the system, as in a turbine. So that's the sign convention for that. And these magnitudes are always positive for the same reason that dragging my briefcase across the table uses up energy either way you flow. And so those are the issues. Yeah, so that's it. And so what we've done is we've spent some time talking about these Moody charts and what they might represent. And so we know exactly what they look like. You see here that as you get progressively rougher pipes, the transition from laminar to fully turbulent, when this line is flat, occurs later and later. And in fact, this transition for a smooth pipe here, this one here is epsilon over d equals 0 in the limit. That's what smooth means. And so you see those. Turbulent, it's horizontal, don't have to worry about the Reynolds number. Laminar, you do, and so we have to think about those behaviors when we solve problems. Okay? So this chart is for circular section pipes. And so we don't always have the luxury of dealing with circular section pipes. And so there are ways for us to be able to make a conversion for that. So we'll talk a bit briefly about that this morning, non-circular sections. We won't recap because we already recapped. And then we'll talk about some examples of solving the easiest solutions where you calculate pressure drop as a function of flow, exactly the example we did last time. So take note of the example we did last time. And then also we'll talk about the more difficult cases where we have to figure out what the flow rate or the geometry of the piping system is, where we don't know the flow velocity, and therefore we have to iterate to a solution. So those are the systems. Okay. So let's talk first about non-circular sections. We won't talk very much about turbulence, only in passing. Non-circular sections is pretty straightforward. The idea is that if you have a pipe that is no longer, or a conduit which no longer is circular in section, then how do you deal with it? We have a variety of factors that have to be defined in terms of an equivalent length. And so what we can do is we can use equivalent Reynolds numbers, and we can use equivalent pipe diameters to be able to figure out exactly what the magnitude of the equivalent friction factors would be. And so typically for non-cross-circular pipes, this constant that we've used for a circular pipe, which is 64, which is just the gradient of this line here, right? In the Moody charts, this is friction factor. This is 64 over Re, which is just the equation for laminar flow within a pipe. This number isn't 64 anymore, and so again we have to rely on experiment or some analysis, I guess, to be able to do that. But it's really pretty straightforward. All we do is we make a substitution, and that the equivalent length dimension that we use in the Reynolds number, or that we use in the roughness, relative roughness magnitude, and that we use in the head loss, is just the hydraulic diameter. And we define the hydraulic diameter as 4 times the cross-sectional area of the pipe multiplied by the perimeter of the pipe. And so for a circular pipe, for instance, 4 times the area is pi d squared upon 4, right? And the perimeter is 2 pi r or pi d. And so when you multiply that out for the case of a circular section pipe, you recover the diameter of the pipe. But what it gives you is it allows you to be able to calculate what that equivalent diameter is if it's not a circular section pipe. But it does, of course, return the correct diameter if you are using a circular pipe. And so the way to do the calculations is to use Moody charts, but to use appropriate magnitudes of an equivalent diameter for those particular cases. So it's nothing more than that. And so we'll do some examples with that also. For some very specific shapes and for laminar flow, you can get those magnitudes. They're tabulated. As I say, this is just really a recipe rather than anything else. And so if you have pipes that also have an annulus in them, which is concentric with the exterior diameter, then you can get the magnitudes of the this, at least for the laminar flow behavior. Right? So friction factor is equal to this over the equivalent Reynolds number. Then, depending on the ratios of the internal diameters, you end up with some appropriate friction factor, which isn't 64, but it's a different number. And of course, if you look at the progression of these, this is one that's almost completely filling, right? So when D1 and D2 are the same, then these are almost the same size, and there's almost no gap whatsoever between them. And actually, you're really looking at flow. If you would take out this, if you expand this inner core out so it's almost touching the outside, then the actual flow area is a tiny portion right here. And so if you unwind that, you basically have flow between parallel plates. And actually, this equation of 96 is the appropriate friction factor for flow between parallel plates. It just turns out to be that way. The other thing is that you can see that as you get to be a smaller and smaller core, in other words, D1 goes to 0, so it shrinks to nothing, then you're progressing almost to, this is going close to 64, which is what you'd expect it to be, right, as you completely remove this. What it's doing, of course, is if you have any kind of core in here at all, is it basically makes the velocity in the center of this pipe 0, because it's clinging to this needle as it's flowing along, because that's the boundary condition. And so I suppose if you looked, can't really draw this very easily, if you took a section through here and you looked at the velocity along that section, so this is velocity, then I guess you know that at the walls the velocity is 0, and if you have a needle in the middle, the velocity will also be 0. So your velocity profile would look like this. Look like a camel. 2 humps. And so that's the reason that this isn't 64. If you got rid of this needle completely that was in the center, then it would look like this, with the maximum velocity in the middle. The parabolic flow velocity that we expect. And so that's the reason that this doesn't quite get to 64, even though this number is really very tiny. It's trying to get to 64. If it is 0, then it would be 64. Likewise, if you have a segment which is has a flat on it, if the flat goes to 0, you'd expect again to reconnect with the one for a circular pipe, and you can do them also for magnitudes of a rectangular section duct. And so I suppose again here these different dimensions are the height of the duct and the width of the duct. If you take a duct that starts looking like this, and we know that the value here is 96, then the same happens here. So in other words, where B is much greater than A, it'll look like this, right? It'll look like this behavior here. And not surprisingly, this magnitude that you get here is exactly the same as the number we had here, just because they're the same geometry. One happens to be a thin slither around the circumference of your tube. The other one is kind of unwound, if you like, but the same thing. This would also look like a very thin duct that you're flowing material into the board on, and this is just of some aperture B, and it's of some aperture A. Did I mean that? Yeah, it's the other way around, isn't it? No, that's right. No, that's right. That's right. B much bigger than A. Yeah, don't cross that out. And so A is small, but B is very large. And so if that's the case, then if B is much bigger than A, then this should go to 0, and this should be the proper one. And likewise for different shaped ducts. So it's nothing more than that. So these values are for the case where you want a specific number to do the laminar behavior. But if you want to use it in a general way, what you can do is you can just roll back and you can use an appropriate Reynolds number that uses the appropriate hydraulic diameter. So you can calculate this for any geometry. You can calculate the equivalent Reynolds number. You can calculate the equivalent loading in this parameter, in the head loss, and you can calculate the relative roughness. And from the Reynolds number and the relative roughness, this one, I'm drawing with my finger here instead of the pen, which is interesting. From those two numbers, right, you can go back to the Moody chart and you can figure out exactly where you should be if you know. So if you know an equivalent Reynolds number and you know what the equivalent relative roughness is, then you always have the ability to be able to figure out exactly what the friction factor is. So, in some cases you can get a number for it, for the laminar cases, but more generally you can just skip back to the Moody chart. So that's it. So we know everything maybe we need to do to be able to make some calculations. We said there were three types of calculations, changing in order of complexity. The one we did on Friday, which was for our JetLev, if you recall, was the first type. So in other words, you can think of these as a matrix of the things that you want to determine, and therefore the other things are the things that you already know. So the easiest one is where you know velocity or flow rate, because if you know velocity or flow rate, then automatically you know Reynolds number. Sorry, if you know velocity or flow rate and you also know the geometry, then you also know Reynolds number, because Reynolds number is velocity, density, some characteristic length, and viscosity. So if you know your fluid properties and you know your velocity and your geometry, these two things here, then it's a straight shot. You do it in one shot. You go to your Moody chart, you know that on this chart, if you have Reynolds number versus friction factor, and the chart looks like this, then all you do, you have a Reynolds number, so you have a friction factor, and then you solve it in one shot. And you solve it in one shot using this expression that we've already talked about today. So that's the easy ones. The more difficult ones are where you want to determine what the velocity is, and you know what the pressure drop is across the system, and you know the geometry. And the difficult there is that if you want to calculate either the flow rate or the geometry, size the piping system you want to use for a particular flow rate, then in either one of these cases, you either don't know the velocity, if you're trying to determine the velocity, or you don't know the geometry, if you're trying to determine the geometry. And so you can't go in one shot to be able to do that. And so the difficulty becomes for those second cases. So what we'll do is we'll go through some examples, some quick examples to look at each of these different types. We did one last of the type 1, and then see how we can solve those. And we'll get as far as we get today to do that. But the basic issue is that for these last ones, if you're trying to determine the velocity or the geometry, either one of those parameters you don't know in Reynolds number, and so you can't go directly to the Moody diagram in one shot to solve for it, and you typically have to iterate on the solution. Okay? I'm not going to talk about that. So let's do a couple of examples, and it's pretty straightforward. Fine. And so these are taken out of the book. They are for the first case, which is a simpler case. And so we know we have a duct of some size. You know the size is 0.3 of a meter by 0.15 meters. You know the flow rate that you're going to get along it. And so you want to determine how much is the head loss over 12 meters. And so the head loss is just this in general. And we have to figure out exactly what the appropriate parameters would be. We need to know the length of duct. We know that. We need to know the equivalent hydraulic diameter, which is a square section duct, so we need to calculate that. It's 4 times the area divided by the perimeter. So 4 times the area would just be 4 times A times B, right? 4 times A times B, which is the area. The perimeter is just going to be 2 times 0.3 plus 2 times 0.15. So this here is the perimeter on the bottom. I guess the whole thing is the perimeter, right? 2 times that. And so we have an equivalent hydraulic diameter. So we have that. We don't know yet what the friction factor is. We do know what the velocity is going to be because we know that the velocity is equal to the volumetric flow rate divided by the area, cross-sectional area. And we know this area is going to be this, 0.3 meters times 0.15 meters, which is just the cross-section of the duct. And so if we know what the volumetric flow rate is, we can get a velocity for that. So we have a velocity here, which is 1.51 meters per second. We know gravity. We know this is 12 meters of duct. We have a hydraulic diameter for this, which is 0.2 meters. And the only thing we have to figure out is going to be the value of the friction factor. And so how do we get that? Well, two things. We know that on our Moody charts, we're going to have to, there are two parameters that describe our behavior. One is the Reynolds number, and one is the, depending on where we are, the relative roughness. And so we need to calculate, I think, both of those. So Reynolds number, for the equivalent Reynolds number, we always write Reynolds number as equal to velocity, density, a characteristic length, which is always the diameter of the pipe, and a viscosity. You can also use, this is dynamic viscosity. You could also write it in terms of kinematic viscosity, where kinematic viscosity is equal to dynamic viscosity divided by density, just by definition. And so if you do that, then you end up with this term here, right? This is kinematic viscosity. Don't know why, well, I guess you use it because there's one parameter that goes into Reynolds number rather than two. And so it's usually defined for a particular gas. And so we know what the velocity of flow is, which is this number here. We know what the equivalent hydraulic diameter is, which is this number here. And we need to get the value of kinematic viscosity. I know dynamic viscosity, well, what would it be? So, actually for air I don't know. I know the viscosity for water. It turns out to be this number. So you can look it up in your tables in your book, or you could Google it, I suppose. And so you end up with a big Reynolds number. So this is 2 times 10 to the 4. So we know a Reynolds number, but we don't know what this relative roughness is. And so again, the relative roughness is whatever the absolute roughness is, which we don't know, but we do know it's galvanized iron pipe. And so again, it's kind of a recipe, and you go back in your book to look. I think there's some charts. There's a table. We didn't really spend any time talking about it. Now is the right time to talk about it. This is it here. So, galvanized iron pipe. So, equivalent roughness, I guess, is 0.15 millimeters. It's metric, so that. I guess the other thing is that these roughnesses are just included on this nomogram. So if you have galvanized iron pipe, which I guess is this one, or galvanized iron, yeah, is that duct? I guess it's pipe. So it should be on this curve here. And so if you know your equivalent diameter, what was it, 0.2? Oh, that's in inches, I guess in meters is here. So it was 0.2 meters. I should use this again. So I think it was 0.2 meters was our magnitude. So hopefully going up here to this point and then going across to here. It's just the same as calculating using the 0.15, I think. It should be something like 5, 6, 7 times 10 to the minus 4, is that right? In terms of relative roughness. Let's see if that is actually what it is. So it's a non-dimensional number. And what number did they have? 0.15, remember, was the absolute roughness of galvanized pipe. Yeah, so they have it here. So they haven't used that, but this is 0.15 millimeters, which is 0.15 times 10 to the minus 3 meters, and this is dH. So you have a number here, and so you have from a relative roughness of 7.5 times 10 to the minus 4, and a Reynolds number of 20,000. So let's see. So it's just recipe. So 7.15 times 10 to the minus 4 is this one, is it? I'm guessing that's what this is. This green thing is here. So 1, 2, 3. Yeah, this is this one here. This curve. The Reynolds number was 20,000. So 1,000. So that's this one, right? Is that? And so if you follow this along to wherever it's going, it's pretty much a smooth pipe. And I guess that's what this green one is here. Yeah, I guess that's what this is here. This green arrow here is exactly that. If you go up to here, yeah, you kind of lose the resolution, but you come across here and you end up with a value of 0.0256728, something like that. This number here. And hopefully that should be the number that you use. So 258. So yeah. So this is the friction factor. This is the length. This is the equivalent diameter, and you end up with a head loss of 0.18 meters. So it's no more than that. Same deal, I think, for the second one. I'm not sure whether it's worthwhile doing that. Is there anything any different than that? You have a volumetric flow rate. In this particular case, it's in English units. You want 500 feet of the duct. It's exactly the same. So no different. So it's just a recipe. And so you have to be able to calculate an equivalent Reynolds number, which is what we did. And you have to realize what the equivalent roughness of the pipe is, or the duct is. And that depends on the magnitude of the material that you're using. So the first ones are straightforward, exactly the same as we did. So last time we did one that had a pump in it and also some head losses in it. So we know how to do at least these ones, and so it's relatively straightforward. When you deal with the ones which involve an unknown velocity or an unknown geometry, it gets a bit more difficult because you have to actually iterate towards a flow system. So maybe I'll split this up into two videos. But so when we're talking about pipe flow, the other more difficult cases to do are flow rate and geometry that we wish to define and we don't know. And so there are some examples. I've just taken some out of the book to do that. What is this? Is this a type 1? I think it's probably... it's not a type 1. It's really a type 2, isn't it? So well, let's look at the question. So you have a big pipe here which is tapped. So a big reservoir, which might be a pipe going into the screen, which is tapped by another pipe of a smaller diameter, 0.02 meters in diameter. It has a T in it, and in that T it has a so-called surge chamber. So the idea here is that if you have water flowing out of this larger reservoir through this valve, and you suddenly shut this valve, all of a sudden you stop the momentum of all the fluid coming down here, and it's probably not much of a problem in just a household flow system. But if it's in a large dam, for instance, they have surge towers or surge chambers, which is a reservoir maybe a few hundred meters high, the turbine house built into the mountain, and linked by a tunnel. The tunnel at the bottom end is typically steel lined because it has to take relatively large pressures. And when you shut off the turbines to be able to stop the generation of electricity, then all of a sudden you have all this water which might be coming down in a tunnel that might be 3 meters in diameter, 10 feet wide, and traveling at tens, I don't know if hundreds of meters a second, but tens of meters a second. All of a sudden you shut the door and all of a sudden it has to stop. And so rather than stopping and kicking the door out, we saw some examples of a plant in Russia where basically the whole underground turbine hall exploded because of something going on. I'm not sure exactly what it was. But to be able to take care of all that energy, typically what you have is a surge tower. And so in hydroelectric schemes, you have a tunnel which is driven vertically upwards, which just has, which may actually go up to issue into the air. but it may also be closed. And if it's closed, it just has an air cushion. So that when the water is ramping down here and you suddenly close it off at this valve here so it can't go, it goes up into this tunnel, it compresses the air, and it loses its momentum in a relatively orderly way, more slowly than if you just shut off the valve directly. So a surge chamber is something that perhaps you have in piping systems, I don't know, but certainly you have them in large hydroelectric dams as part of the makeup. And so what are we trying to do here? We start off with the valve closed, and we know that the pressure in this whole system in this valve is everywhere equal to 400 kPa. And at that stage, we know the height of the surge chamber is 0.4 of a meter high. And so we have a certain amount of air in this surge chamber under that pressure. When we open up the valve here, then the supply remains at 400 kPa. But now, all of a sudden, it's issuing to atmospheric here, and so we'd like to be able to figure out exactly what the change in pressure is at this point here. And as a result of the change in pressure in here, what is the change in elevation of this surge chamber? So that's kind of the two-step process. So the valve's fully opened, the pressure at point 1 remains the same, but it goes to atmospheric here. If we know what the characteristics are of the tubing, how do we calculate exactly what the height of this gas is in here? And so it seems relatively straightforward. It's going to be driven by the magnitude of the pressure that we calculate here. So the pressure at this point is going to start off at 400 kPa. We're going to open the valve, and all of a sudden it will be at a different pressure. Presumably it will be lower, because this will be at atmospheric. If this is at a lower pressure, then what it would allow is it would allow this column of water here to change in height, and as a function of that, it will change the magnitude of the pressure within this air. And the only thing that we know in this surge chamber is the change in mass is 0. Right? So the mass of air that we have within the surge chamber isn't going to change. But the pressure of it is, because it's going to expand as we change the pressure at this particular point here. So that's kind of the essence of this question. So it's an interesting question, I think. So how do we do that? Well, the easiest thing first is to figure out exactly what the pressure should be within the system. So we don't know yet what the flow is in this system. So it's not really type 1, right? It's probably type 2 in our classification. We don't know the flow rate. What is the flow rate? Well, we can write Bernoulli between points 1 and 2. So point 2 is downstream, point 1 is upstream. So the pressure at point 1 is 400 kPa. What does it say? Is the magic word in there? No. It doesn't say large pipe, but this velocity here is, if it's large, we can make it equal to 0. So make that 0. If the elevations of both of these points are the same, then we don't need to worry about those. What's the pressure at point 2? Pressure at point 2 is atmospheric, if it's open to the atmosphere. We don't know the velocity at point 2 yet. And we know what the characteristics are of the friction factor, and we know the length of piping, and we also have a couple of fittings in there. So we need to know the magnitudes of these as well. So major losses, minor losses, and the velocities of flow within the pipe relative to the velocity of flow within the nozzle here. And it's no different. The nozzle, I think, is the same diameter as the pipe. And so what do we know? We need to know what this friction factor is. We know. We need to know what the friction factors in the fittings are. And so you could go back to your tables and figure out, they're given right here, for the angle valve, which is this, which is 2. And for this valve, the loss coefficient is equal to 0.9. And so if we rearrange this, we know this. We don't know the velocity. We do know the friction factor. The length of pipe is going to be 5 plus 8, which is 13, right? Divided by this diameter, which we also have. And we also have this. We know that this velocity in this fitting here is the same as the velocity in the pipe. So it makes life easy for us, I think. And so we can combine this expression. So we know this value. We know this value. We don't know what the velocities are. They're equal to each other, and so we can just rearrange here. So this expression here is just, this is P over GAM, unit weight. This, which is equal to this, and we've just isolated this velocity term there. This is the fitting, this is the T, this is the faucet, this is the loss in the pipe, so this is the major loss. And this is just this term here coming out of the pipe. So this is the flow at the downstream end, the major losses in the pipe, the two minor losses in the pipe. So that gives us a velocity. So if we've got the velocity, now we want to be able to figure out what the pressure is here, because that's going to control exactly what the magnitude of this pressure in the surge chamber is. So what we could do is, now we know the velocity, we could write Bernoulli equation between here and here, or we could write it between here and here. I think you could do either one. In this particular case, it's written between point 1 and point 3. So I don't know whether you could also do it between point 2. But certainly we know the conditions here, and we don't know all the conditions here. We know a velocity, we know an elevation, but we don't know a pressure. We'd like to know the pressure. Here we know the pressure, we know the velocity is 0 because it's a big pipe, and we know the elevation. So I guess if we write it between these 2 points, the only thing we don't know is the pressure at this point. And so that's exactly what this is. Bernoulli written between the upstream, 1, 1, 1, 3, 3, 3. Now the length of pipe that we have is only going to be 8 meters, right? The loss that we have is really only one fitting, which would be equal to this 0.91. Or I guess you could make a point that it could be half of that, because it's flowing through half of it, doesn't really matter. And what else? So the only thing, we know this is 0. We know this and this disappear. We know the magnitude of the velocity. The only thing we don't know is this. So we can calculate the value of the pressure at 0.3. And so certainly we know the pressure of the unit weight. And so we solve for the magnitude of the pressure. Won't go through the math, but you see the values in here. I'm trying to look, where's the value that's been used for this. Oh, they use 0. Yeah, I guess 0 because it's, yeah, I'm not sure necessarily I'd have used 0, but anyway, they've used 0. So I would have used half of it actually, but anyway, it doesn't matter. So you have some value to this, and you end up with a pressure which is equal to this magnitude here. And so you have two conditions. You have a pressure originally at P3 was equal to 400 kPa when it was closed. And you know that when it was at that pressure, this height was equal to 0.4. And so that's one condition you know. The other condition you know is that when the valves open, the pressure is equal to 187 kPa. It's less, of course. When it's closed, you could imagine the pressure all along here is equal to this amount. When it goes down at the left-hand side, then it correspondingly should go down not to 0, but the magnitude of the pressure here, you'd expect to be somewhere between the 0 pressure here and the 400 kPa pressure here, and it's roughly half of that, not quite. And you know that the value, for in this case, is the magnitude of H3 is equal to what? You don't know. And so what you want to know is to be able to link those together in some way. And so the only thing that you know is that mass of air for open is equal to the mass of air closed. So in each of these cases. And so what these are, they're joined by the amount, this is just a little diagram of the air cap, if you like, in the surge chamber. And you know the total height of this surge chamber is equal to 0.5. This is the height of the water that's in there. And so the amount, the volume of the air cap is going to be equal to 0.5 minus h times the area of this tube, right? And so what you can use is you can use the ideal gas law to basically write the density times the volume. So density times volume is going to be equal to kilograms per meter cubed multiplied by meter cubed, which is equal to just the mass. Right? So if you can get the density of the air and the volume of the air, then they have to be equivalent to each other because the gas can't get out of there. And so what you can do is you can write the behavior in terms of the product of the open and closed cases. So these expressions here are just equal to the mass of air in both cases. So the density of air times its volume has to be the same in both cases. If you substitute for the density of air in terms of the ideal gas law, pressure when it's closed over gas constant times temperature, pressure when it's open, ideal gas constant times temperature, multiplied by the volume. This is just this volume here, right? And so if you equate these two magnitudes to each other, then you can make assumptions that the temperature doesn't change, the gas constants cancel out on both sides, and so you can use that to be able to solve. This is pressures, not density, right? So this is the pressure at this point. This is the pressure when it's closed. You know those magnitudes because you have the magnitude of the pressure at this point, and you can go up some amount here to get the pressure at the bottom of this gas cap just by subtracting off the elevation times the unit weight. And if you do that, you end up calculating kind of a long-handed way the magnitude of the height that corresponds to the case where you have this different pressure acting at the bottom, nothing more than that. And so the issue is that there's a balance between the pressure here and the pressure that you have here because it's constrained by the fact that the mass of air can't get out because it's left in the system. And if you go through this kind of long involved calculation, you end up with a height which is equal to 0.28 meters instead of 0.4 meters. So in other words, you drop the pressure in the pipe, the air expands because of because compressible fluid, a gas in other words, and you can calculate the magnitude of the pressure at this point, which is constrained by the volume of air. So perhaps more involved than we really wanted to do. We'll perhaps leave it there. So the point is that if you're dealing with this is a relatively straightforward one. Well, it wasn't straightforward because of the surge tower, but if we were calculating only the pressure at that middle fitting, it was relatively straightforward because we were given a magnitude of this friction factor. So the one thing that made this life really easy for us was the fact that we didn't have to iterate on the solution because we're given this magnitude. So physically what this means is that the flow in the pipe is really turbulent, right? Because if the friction factor is given as a constant magnitude and it doesn't change at the velocities that we're at changing velocities, then we know that if we're on the Moody chart, then the location where we are is we're somewhere on this side. We're somewhere here. And so it needs to develop a physical feel for that. So it's important to understand the reasons for these different regimes. And the fact that if you are given the magnitude of the friction factor being constant, then it probably means that you're kind of in this region here, right? Because these are all horizontal.